Alright, so today we're talking about ecosystems and the biosphere. So ecosystems, what is an ecosystem? How do we define that? So this is just another level in the hierarchy of organization in biology. So we talked about organisms. Then we talked about populations, which is a group of the same species of organisms. Then above that was communities, which is all the living organisms in an area of all species. What do you suppose an ecosystem includes that the community doesn't?
The environment.
Yeah, the abiotic environment. So this is just another level up in the hierarchy of organization, and now we're talking about things that, or we're including things in the conversation that aren't alive. So the abiotic environment includes things like air, water, soil, rocks, stuff like that. The biosphere is the next level up, and that's the entire planet. So an ecosystem includes all the living organisms in an area, plus the non-living abiotic environment, the air, rocks, soil, water, what have you. Now an ecosystem, it's important to note, can vary in size. It can be basically any size you want it to be. If you're the ecologist studying the ecosystem, you define the parameters of your study, and that's what defines how large your ecosystem is. It could be something as small as one single tide pool at the beach. That could be an entire ecosystem depending on the scope of your research. Or it could be the entire Amazon rainforest if you want to do a really big study. But the important thing to remember is that there's no set size for ecosystems, and they're determined by the scope of the study we're talking about. Ecosystems also have very complex ecology. So as you get into higher and higher levels of organization and you're including more and more things, then you have to start considering much more complex and many more interactions. So when we're looking at population ecology, we're only looking at one species. We're only looking at the interactions between members of that species. When we go up to community ecology, we're looking at all the living things in the area. So now we're looking at much more complex interspecific interactions. Now that we're talking about ecosystem ecology, we're also including not just interactions between and among different organisms. Come on. Probably need to charge this thing. But we're also looking at the interaction between organisms and their physical environment. So now we're not just talking about the way life affects other life, now we're talking about the way that non-living factors also affect life. Like, you know, if there's decreased rainfall, or if there's increased temperature, or if there's a massive nutrient influx in the ecosystem, now we have to include things like that as well. There are many different types of ecosystems as well, depending on how specific you want to get. One of the most important ones is the marine ecosystem. You guys are all familiar with that term? You know what I'm talking about? Yeah, marine ecosystems are things in the ocean. For one, this is the most common type of ecosystem on Earth. So roughly 2/3 to 3/4 of the Earth's surface is covered by water. So the vast majority of ecosystems on Earth are marine. There are also aquatic ecosystems, but they only make up like 1% of the world's ecosystems because lakes, rivers, streams, and what have you don't really account for that large of a proportion of the planet. In addition to being the most common or most abundant type of ecosystem, marine ecosystems could be considered to be the most important, especially for any aerobic organism. Why do you suppose that is? Yeah, so the marine ecosystem produces the majority of the world's oxygen. So phytoplankton living on or near the surface of the ocean photosynthesize, giving off oxygen. We may not think about it much because they're these tiny microscopic organisms, but it turns out that they actually account for the largest proportion of all oxygen production on the planet. You also have 3 basic types of marine ecosystems. We'll get more into that later on in the lecture, but you can basically divide it up into coastal parts, open ocean, and seafloor. Also mentioned freshwater ecosystems, not quite as important because I shouldn't say they're not important, they're just not as abundant. And then terrestrial ecosystems, which is what we probably think about more often than anything else, because that is where we live. when talking about terrestrial ecosystems, we can categorize them into various biomes that are characterized by certain specific traits that we quantify as we're looking at these ecosystems. Come on. There we go. But it's important to note also that these biomes tend to be very broad categorization. Like when I say biome, I'm talking about tropical rainforest, we're talking about desert. But that doesn't mean that all tropical rainforests look the same or that all deserts look the same. You can see here, these are both desert biomes, but they are extremely different. So these are very general classifications, and there can be a lot of variation within the same types of biome, depending on what part of the world you're in. Any questions so far? Pretty broad overview at this point. I briefly mentioned last time when we were talking about succession that ecosystems can be subjected to disturbance, and this happens fairly often. Now, a disturbance is basically any change in the environment that affects the composition of the ecosystem. So it may be anything that affects biodiversity or species richness or the size of certain populations. Now, it can be fairly mild, like something like slightly decreased rainfall for the season could be classified as a disturbance because it will change the composition of that ecosystem based on which plants are or are not able to grow in conditions with less water. They can also be extremely severe, like a hurricane or an incredibly catastrophic forest fire. They can also be non-natural. Ecosystem disturbance can be caused by people if we go in and clear cut a forest, for instance. Now, before I move to that point, everybody remembers what succession generally looks like, right? Succession is the recovery of an ecosystem following a disturbance, where you'll have certain pioneering species come in and reestablish themselves, which eventually give way to other species as succession progresses. Succession also is based largely on the severity of the disturbance. If you have a ridiculous, enormous disturbance that scrapes everything down to bare bedrock, no soil even left, that's called primary succession. As long as you still have dirt, then it's secondary succession. All right. Now, a concept related to disturbance is equilibrium. So when ecosystems are not experiencing a disturbance, they are said to be in a state of equilibrium. Who can define equilibrium for me in a general sense, not even in the context of biology? Yeah, I think most things are basically staying the same. There's no big changes in anything. So when an ecosystem is in equilibrium, or when it's said to be in equilibrium, that means that biodiversity remains relatively constant. Not absolutely constant, there's going to be some fluctuation, but there's not going to be any major swings. And there are two parameters that we use to study changes in an ecosystem as a result of disturbance. Does anyone know what those are? Who's read this far in the book? So one of them is resistance. The other one is resilience. And they're mainly what they sound like. So if we're measuring the resistance of any ecosystem, that is its ability to remain at equilibrium. So a highly resistant ecosystem is going to be able to resist changes as a result of disturbance, basically. Resilience, then, is the ability to return to equilibrium following a disturbance. So these are two different characteristics. Now we can sort of tie this back into our selected and K-selected species. So if you have a lot of K-selected species in your ecosystem, you're probably going to be relatively resistant to disturbance. However, if there is a massive disturbance, it's probably going to take a long time to get back to equilibrium, because those K-selected species don't tend to reproduce very rapidly. On the opposite side of that coin, if you have a lot of R-selected species dominating your ecosystem, you're probably not going to be all that resistant because they can be killed off much easier, but you are going to be, your ecosystem is going to be more resilient because you have these species that are capable of very rapid population growth. So generally, ecosystems tend to shift or tend to lean more one way or the other. Highly resistant ecosystems tend to be less resilient. Highly resilient ecosystems tend to be less resistant. Does that make sense? Great.
You could change your scope of that, right? Like depending on like if you're talking about like the well, you were talking about like different species, but the ecosystem you have both case-selected and R-selected.
Yes, yeah, any ecosystem is generally going to have case-selected and R-selected species present, but in most types of ecosystems, you will see one of them be more dominant than it is in other types, or maybe more dominant than the other. Like if I'm talking about the redwood forests in Central California, really dominated by gigantic case-selected redwood trees. That's going to confer a lot of resistance to disturbance in that ecosystem, because if you go a couple months with lower than normal rainfall, those trees have enough water stored in the tissues to survive. If you have a fire come through, those trees are large enough that most of them are probably going to survive the fire. So they tend to be more resistant. Now, if you are talking about the grasslands in Wyoming or something, if you have lower than normal rainfall, the grass are going to die from that drought a lot faster. Or if you have a fire rip through, that's going to wipe out all of the grass. So that's sort of an example, extreme examples of an ecosystem that is more dominated by case-selected species being more resilient or resistant, and another ecosystem that's more dominated by R-selected species being more resilient or less resistant. Does that make sense? Okay, great. So when we're talking about ecosystems, one thing that we really have to talk about is energy, because all life requires energy. Any biological process has to be driven by some source of biological energy, generally in the form of adenosine triphosphate. So where does the energy in ecosystems come from? Yeah, usually the sun. There are a few counterexamples in, benthic seafloor communities where they get it from chemical sources. But for the most part, it originates from the sun. What traps that energy into a biologically available form? The primary producers. So in most cases, those are going to be the photoautotrophs, except in those few examples, or few exceptions I mentioned, where it's going to be chemoautotrophs. But what ends up setting the energy budget for any ecosystem is the amount of primary production, the amount of sunlight that gets captured and used to make sugar, for example. Now in that, when we're talking about this, it's important that I mention both gross and net primary productivity. So gross primary productivity is just the amount of energy that gets captured by the autotrophs, the producers. However, not all of that is going to be available for other organisms because those producers need to use some of it for themselves. So the net primary productivity is the gross primary productivity minus the amount of energy used by those producers. That's what's actually available for the rest of the community. Energy flow is another important concept. So in ecosystems, energy makes a one-way trip. It comes in usually from the sun. In fact, I'm just going to say from the sun because we're not really looking at benthic seafloor communities right now. So energy comes in the form of these nice warm sun rays that get absorbed by these photosynthetic plants that use that energy to drive the synthesis of sugars, storing that energy in a biologically usable form, in a biomolecule. Then those delicious sugars get consumed by, I don't know, let's say a deer. And then that deer stores some of that energy in its own tissues. And then that deer gets consumed by, let's say, a mountain lion. And that mountain lion stores some of that energy in its tissues. But it's going to end up using most of it for its own biological processes. And it's eventually going to be lost as some unusable form, usually heat. Remember that cellular respiration is only 36% efficient. So you have about 64% of all the energy consumed just getting radiated out as heat, which is lost to the ether in space, never to be seen again, and can never be used by any other biological organism. So that's why energy makes a one-way trip. Yes?
How for sure is that, like, that it
it is, unless our understanding of physics is completely wrong, it's 100% certain. Or, well, nothing's ever 100% certain, but we're as certain about that as we are about anything. That's due to the second law of thermodynamics, if everybody remembers that, which states that entropy will always increase at any given opportunity and never decrease, entropy being a measure of disorder. So anytime you convert energy from one source to another, you're going to lose some of it to entropy. And that will never be captured again, will never be reused. It's just gone forever. So the energy comes in from the sun, gets harnessed by the producers, goes up through the different levels of the food chain, and then gets lost and never comes back. It's a linear trip. Nutrients, however, don't do that. They get recycled in ecosystems, which is important because we don't have a constant input of nutrients like we do with energy. The sun is bathing us with glorious free energy all day, every day, but we have a relatively limited amount of, let's say, carbon or hydrogen or oxygen. We have very small inputs of chemical elements in the form of meteors hitting the Earth, but that's not very significant when we're talking about the scale of the whole planet. So nutrients have to get recycled, otherwise everything grinds to a halt. Any questions on that so far? Or any other questions? Okay.
Actually, yeah.
Yes.
So the loss to entropy, so that's basically, so we're trying to convert something, or we have the energy source like the sun, obviously, and then it gets picked up by plants and all that, easy plants. So whenever anything's converted, you're never actually going to fully gain all of that 100% energy transfer between those. But then the nutrients getting recycled, if I'm understanding is correct, is kind of more like a matter be created or destroyed type of thing, or?
What was that last part you said?
The nutrients get recycled, the second part of it, so it's more of like a matter can't be created or destroyed kind of thing?
Yeah.
Okay.
Yeah, so like, when you eat some cane sugar and you're digesting those glucose molecules using it for cellular respiration, some of that energy will be lost, but the actual chemical atoms within that molecule will never get destroyed.
Okay.
So they just get recycled into different forms, for the most part as carbon dioxide and water. Good question. All right, any other questions before we move on? Okay, so now to talk a little bit about food chains and food webs. I'm sure you guys have all heard of a food chain. You're all relatively familiar with that concept, right? We like to say that we're on the top of the food chain, which is generally the case unless we go out into the ocean or something, then we're not the top of the food chain anymore. But food chains are just a linear sequence which describes the flow of energy through ecosystems. They have multiple trophic levels. When I say trophic level, that basically means what level of the food chain you're on. So at the bottom you have the producers, basically the photosynthesizers. Then things that eat them are considered primary consumers because they're eating the producers. Then obviously there are going to be other animals that eat the primary consumers, so we call them secondary consumers. Then there are things that eat the secondary consumers. At the very top, we have tertiary consumers, which are also called apex predators because they are at the apex of the food chain. Come on. Just too far out. Now, what level do you suppose you are at?
Why do I feel like we could be on multiple levels?
Because that's true. So a lot of organisms end up eating at multiple different levels of the food chain. The only people who are at strictly one level of the food chain are vegans. People that only eat plant products are primary consumers. Anyone else is some mixture of multiple other levels. All of us are at least partially primary consumers because everybody eats at least some plant matter. Most people also eat some meat. Depending on what meat that is, it could be, you could be a secondary consumer or a tertiary consumer. So I mean, if I'm having a bacon cheeseburger for lunch or something, I've got bread, so I'm a primary consumer, and hopefully some vegetables. I've got beef, so I am a secondary consumer because that cow is a primary consumer. You got some bacon in there from a pig, which is a secondary consumer. So you're also a tertiary consumer. So whenever you're calculating the trophic level of any organism, it's very complicated to do it accurately. You have to basically take proportions of its diet that come from each level and then average it out. I'm never going to make you do that on a test, though. I just want you guys to understand the concept. Any questions on this before moving on? Okay. Does this food chain seem really accurate and descriptive? No, of course not. It's a gross oversimplification of what actually happens. It's good for general concepts of trophic interaction in ecosystems, but it is a massive oversimplification. That's not what I wanted to talk about next. But I already mentioned that at each level of the food chain, energy is lost. That's because energy transfers are inefficient, and also because you're going to end up using most of the energy in the food you eat to do things rather than investing it in the tissues of your own body, right? I mean, over the course of a human lifetime, how many tons of food do we eat? We don't put all of that into our own tissues, hopefully. Now, it happens to be as much as 90% of all the energy is lost at every level of the food chain. That depends on the growth efficiency of whatever organism we're talking about. On the opposite extreme would be something like a squid, which has like 67% gross growth efficiency, meaning that about 2/3 of the food it eats actually gets stored in its own tissues. We are very far on the other end, where the vast majority of the food we eat is lost as heat or used for motion or used to make noise in my vocal cords while I'm up here bloviating about food chains. So what that means is that each level of the food chain has to be much, much smaller than the level below it. So every level must necessarily contain vastly less biomass than the level directly beneath it, which supports it. So what you end up seeing, and I'm not a huge fan of this image because it has the producers on the top and the tertiary consumers on the bottom, but what we end up seeing is ecosystems that have a huge amount of biomass at the level of the producer. They can only support about 10% of that much biomass on the next level in the primary consumers. They can only support about 10% of that biomass in the secondary consumer level, which can only support about 10% of that biomass at the tertiary consumer level. That's why if you were to go out into a forest or something, you would see enormous, enormous amounts of plants, and you'd see a few little critters running around like squirrels or rats or mice or something like that. You'd see very few things like, snakes or coyotes or anything like that in the secondary consumer level. And odds are you probably wouldn't even see a tertiary consumer like a bear or a mountain lion because there are so few of them. Because all that energy gets lost between each level, so you have to have an enormous amount of things below you to support just a small number of individuals at your level. One of the necessary conclusions of this is that your annoying sanctimonious vegan friends actually are better, because they are using a lot less energy, thereby contributing to less deforestation, less greenhouse gas emissions, less water consumption, less climate change. The lower on the food web you eat, the less actual initial energy investment it takes in order to support it. I'm not saying everybody should be a vegan. I'm not a vegan because meat is delicious. But bear that in mind. So when those annoying vegans are telling you how you're ruining the planet, they're actually not wrong. All right, any questions on that concept? Yes. Oh, my hand's up. Does this make sense to everybody? All right, now here's what I thought I was going to talk about after that last slide. So food webs are a much more accurate representation of trophic interactions within an ecosystem than food chains are. Now, a food web is sort of what it sounds like, where it's an interconnected map of all of the trophic interactions in an ecosystem. Now, even this is a gross oversimplification of the trophic interactions in an ecosystem, but you can already see how it's quite a bit more accurate than food chain would be. This shows much more complex interactions, And it also allows you to illustrate how everything eventually ends up coming back down to the decomposers. So no matter what level of the food web you're at, you're eventually going to be eaten by decomposers. They're going to break down your organic molecules back into inorganic matter. They're going to basically turn you into dirt, and then those nutrients can be reused by the producers and take another trip through the system. I also mentioned a few minutes ago that many organisms will feed at multiple trophic levels. So when you're talking about the trophic level of any given animal, unless it's a strict primary consumer, it may be at like the 2.23rd level of the food chain or something like that. Or if it's higher up, maybe like 2.8 or 3.1 or something like that. Yes?
Are generalists more common than ones that are specified with their eating?
That's, I mean, in terms of number of overall species, I would say yes, because it generally tends to be a more, well, anytime you have a more generalist lifestyle, you're going to be more adaptable to small fluctuations within the ecosystem. Like if you only eat plants, or even worse, if you only eat specifically one plant, then if something happens to the plants, you're much more likely to die off. But if you can temporarily switch your diet to eating bugs or eating snakes or something, then you're going to have a much better chance of surviving minor fluctuations in the ecosystem. So that would be more common in terms of overall species numbers, but in terms of biomass, probably less common. So in terms of biomass, you're going to have a lot more of that in animals that eat mostly or exclusively plants, because just due to that necessary reduction of biomass at each level of the food chain. Does that make sense? Okay. Good question. All right, any other questions before moving on a little bit? So I already mentioned everything is eventually eaten by decomposers. So in a way, you could almost call them the top of the food chain, but then we eat them too. So it's much more complex than that. There's no necessarily top of the food chain. But those decomposers are what allow for the recycling of nutrients so that the ecosystem can survive. Without them, we would have all these chemical nutrients just building up in dead organic matter, which would not be biologically available for the primary producers. So then all the primary producers would die out, and we would die out very shortly after. Makes sense, right?
Is every level of the food chain, would you consider a species on those levels like keystone species for each?
So keystone species are a bit more rare than that. So you may have keystone species at any level. Like the gray wolf in Yellowstone is considered a keystone species because it exerts a lot of regulatory force on a lot of other organisms. If you take them out, then there's this huge cascade of events. The sea otter is also considered a keystone species in like the Northern California coastal ecosystems. They're not at the top of the food chain, but they do prey on sea urchins, which eat lots of algae. So if you knock out all of the sea otters, then the urchins explode and eat all the algae and completely change the ecosystem. So keystone species don't necessarily have to be at any one level of the food web, but not everything is a keystone species. I don't know if I did a very good job describing that. Does that make sense? Okay. Any other questions? All right. So then, come on. Another interesting concept when we're talking about ecology is biomagnification. Has anyone heard about this before? Whether or not you've heard about it, it does affect us. So a lot of this has to do with the inefficiency of trophic energy transfers and the necessary reduction in biomass at each level, and the fact that anything high on the food chain has to eat a lot of individual organisms on the level beneath it. So, I mean, the average person in here, if you're not a vegan, has probably eaten hundreds of chickens and dozens of cows in your lifetime. And that's true of basically anything else in natural ecosystems as well. The top predators, like if you're a bear and you're living on salmon, you're probably eating thousands of salmon over the course of your lifetime, for example. So what this results in is increased concentrations of certain chemicals in the tissues of organisms at higher trophic levels. Now, when I say certain chemicals, I'm talking about things that cannot be excreted from your body. So generally this is going to be things that are fat soluble. Almost any water soluble chemical we can excrete in our urine if we want to. But when it comes to fat soluble chemicals, we have no way to get rid of that. Well, the only way to get rid of that is when women give birth, they pass on some of their contaminants to their babies. Because that's pretty much the only way you can excrete fats from your body. We have no structures in our excretory system that can get rid of this whole thing. Yes.
Even like burning it, like if you exercise or whatever?
Yeah, so even if you exercise it, what that's going to do is it's going to consume the fat, but it's not going to destroy the molecules of this contaminant. It's just going to get re-released back into your bloodstream. So good examples of this are things like DDT, or PCBs, or mercury, or lead. So who here really likes to eat tuna? That's a big yes for me. What's one of the problems with eating a lot of tuna? Mercury. So these are top level marine predators. So tuna can live for decades, 20, 30, 40 years. And they're swimming around the ocean and they're eating hundreds or thousands of other fish in their lifetime. If those little fish each contain a tiny bit of mercury, as the tuna digests them, it's going to absorb all of that mercury into its own tissues and keep it for its whole life. So the older a tuna is, the more small fish that tuna has eaten, the more mercury it's going to have concentrated in its own tissues. So then if you're eating loads of tuna, then you're getting all the mercury from all those tuna and keeping that inside your tissues for your whole life. So at every level, it just gets more and more concentrated. That's what biomagnification is. So in this example from the textbook, they're talking about PCBs, probably in a river in New York would be my guess. And you have these small organisms at the bottom that have very low levels of PCBs in their tissue. But you have a low-level predator that's going to eat a lot of these guys, and it's going to store every microgram of PCBs from every amplifier it eats in its own tissues. Then you have a slightly higher level predator that's going to eat a bunch of those, keep all of its contaminants. Every level you go up, you have these organisms that are eating large numbers of animals below them and keeping all of the contaminants stored in their own tissues. So it just gets more and more concentrated as you move up the food chain. Yes?
Don't you like poop it out?
What?
Don't you poop it out? Because then our bodies be like, oh, we don't need that mercury or whatever. So
Unfortunately not. So the reason that these things are even a concern in the first place is that they can take the place of other elements in chemical interactions within our own body. Like, does anyone know why cyanide is actually so poisonous? So cyanide will preferentially bind to the iron in your hemoglobin before oxygen does. So it's really good at replacing oxygen in a chemical reaction, thereby reducing your blood's ability to bind oxygen and carry it around your body so you asphyxiate. Same thing with arsenic. The reason arsenic is so poisonous is because it can substitute for, I want to say either phosphorus or potassium in chemical reactions in our bodies. So these things end up being sort of accidentally taken up in various biological processes, and that's how they get into your tissues. Good question.
Your body can't distinguish between one and
No.
the other when it comes to absorption.
Yeah. Yes.
What are PCBs?
PCBs are polychlorinated biphenyls. This is a synthetic chemical we invented, I want to say in the 30s or 40s, and it has a few different purposes. One of the big ones is as a flame retardant. So we used to, up until I think the 80s, we used to saturate children's pajamas in PCBs because then if they were exposed to fire, their pajamas wouldn't catch on fire. So I mean, it was a great idea until we figured out that the kids were absorbing the PCBs through their skin, causing endocrine disruption and increased risk of cancer. It's the same sort of thing with DDT. I'll see if I remember what that one stands for.
Pesticide, right?
Yeah, it's a synthetic pesticide that was invented in 1931. Dimethyl trichloroethane, I think. That's not important, I'm just showing off. But it was a synthetic pesticide we invented, and it was really good at killing bugs because it interrupted biological reactions in their own systems and killed them, but wouldn't kill us. We had no acute toxicity to it. So we thought DDT was fantastic. For decades, we'd use it to delouse children or delouse, GIs in the military. You can go and find videos of people literally getting showered with DDT because we thought it was completely harmless for humans. They used to drive trucks around in the summer in some cities in the US just fogging entire neighborhoods with DDT to kill mosquitoes because we thought it was totally harmless for humans. Eventually, we found out that it biomagnifies and it's a risk factor for several types of cancer. So it was banned in 1971. But unfortunately, it's also exceedingly persistent in natural ecosystems because since it's a synthetic chemical, it's a molecule that never existed before, nothing has yet evolved a way to efficiently break it down.
But mercury and lead are, right?
Yeah, these are natural.
Those are natural.
Yeah,
So,
but these are also elements. These aren't compounds. So mercury and lead are, individual elements or individual atoms on the periodic table. So they definitely can't be broken down by any normal chemical means. That's the definition of an element. So like the mercury in tuna, we used to think that these high levels of mercury in tuna were a result of human-induced pollution. And while we may be affecting that a little bit, we've analyzed tissue from really old samples of tuna and found that they still had high levels of mercury. So it's probably more or less natural. All right, some good questions here. Anything else before we move on?
So would the reason why natural selection might not have come up with an animal that can excrete these more like the heavy metals or the elements, would that be because these animals can still live for a long period of time
Exactly.
without it disrupting their life cycle?
So the highest concentrations of mercury you ever see in any natural animal in an undisturbed ecosystem is still not going to be high enough to cause death before reproductive age, or in most cases, even at all. I don't know if there's ever been a documented case of a tuna naturally dying from methyl mercury poisoning. It only becomes an issue when we start eating lots of them because we eat massively unnatural amounts of it. And you get the same thing if you eat any high-level, long-lived oceanic predator. You see the same thing in people that eat dolphin or whale as well, because they tend to have very high levels of mercury in their tissues. So we are our unnatural habits are causing unnaturally high concentrations of mercury in our cells, and that's when it starts to become a problem. Even still though, I don't know if there are any known cases of humans having significant effects of methyl mercury poisoning before reproductive age. This generally doesn't really cause anything serious until very late in life, so it's not necessarily going to be removed by natural selection. By the way, one thing I should mention real quick, all this talk about mercury, you guys have probably heard some anti-vaxxers spouting their pseudoscience about the mercury in vaccines being toxic. It isn't. That's because mercury has to be in a biologically available form for you to take it up. Generally, that's going to be methyl mercury. If it's just elemental mercury, inorganic mercury, it can't be absorbed into your cells. So the chemistry of an element can greatly change when it's in a compound. I think I gave the example really early in the semester about how water, which every organism needs to survive, is only one oxygen atom away from being hydrogen peroxide, which is toxic to basically everything. So you change one tiny thing about a compound, you can completely change the chemistry and how it interacts in biological systems. Okay, anything else before we move on? Great. So biogeochemical cycles. I talked about how energy makes a one-way trip through the ecosystem. And I know that sounds like a really large and intimidating word, but it's actually very simple. So chemicals get recycled in the ecosystem. Those are the really important ones. Come on, where is it? There we go. So this is the basis for that huge word, biogeochemical cycling. So the recycling of chemicals in the ecosystem depends on various biological processes, geological processes, and chemical processes. So there we have biogeochemical cycles. Doesn't sound so intimidating anymore, does it? Great. My friend actually has a PhD in biogeochemistry, and he works for BP making huge amounts of money. I'd probably have trouble sleeping at night if I worked for BP, but he certainly doesn't. Anyway, so the water cycle. This is one of the most important biogeochemical cycles there is. Obviously, because water is absolutely necessary for all life. as we understand it, life cannot exist without water. It's important for every single biological process. Now, when we're talking about the water on Earth, at any given moment, roughly 97.5% of that is going to be salt water. It's going to be in the oceans. So that's not usable for us. It is usable for many other organisms, like marine organisms, but not for us. Now, the cycling of water involves a whole bunch of different processes, most of which are generally weather related. So when we talk about the water cycle, yeah, I didn't really put that in there. When we talk about the water cycle, there's a whole bunch of processes. Like, depending on where you want to start it, we'll say that water initially gets precipitated down onto the land in the form of rain and snow. Then it will be absorbed into the ground and stored as groundwater, or it will run off into streams, which feed into rivers, which feed into lakes, or maybe reach the ocean. It can be consumed by organisms on land, may return to the atmosphere through evaporation off of land. Once it reaches the ocean, then it becomes salt water. Now, that doesn't mean that it's lost forever, because obviously water evaporates out of the oceans as well. But it doesn't take the salt with it when it evaporates. This is how fresh water gets recycled. So you have water evaporating out of the oceans, which condenses into clouds in the atmosphere. Wind blows it back over land, and that causes those clouds to increase in elevation and get colder and condense even more, until they get so dense that the water falls out of the sky again, and we call that rain. So this is the general water cycle. Any questions on this? This one is mostly chemical processes. There aren't really any biological processes involved in the water cycle. Yes?
So is that why you can have, like, say, like the Chilean desert sitting literally right next to an ocean and have basically no rain?
Yeah, absolutely. So a really good example would be Oregon. Anyone here ever been to Oregon? I'm familiar with it because that's where I'm from. But what do you think of when you think of Oregon?
Rain.
Rain. And that's mainly Portland. So in Oregon, you have this range of mountains called the Cascade Range, which is about 50 to 100 miles inland, depending on where you are in the state. If you're on the coastal side of the Cascades, which Portland is, then you get enormous amounts of rain because you have all these fat clouds blowing over the land, which get squeezed by the mountains and all the rain falls out. If you go to the other side of the Cascades, most of Oregon is actually high desert. It's really dry. Because by the time the air gets past those cascades, it's had most of the water squeezed out of it already. So that's why you see very little rainfall, generally in most inland areas in general. Good question. Any other questions? Okay. The carbon cycle. Obviously, carbon is important. Carbon is present in all organic molecules. That's what organic means. That's also why we call ourselves carbon-based organisms, because all of the molecules we produce in our bodies contain carbon. It is also the fourth most abundant element in organisms, behind things like oxygen, hydrogen, and nitrogen. Now, the carbon cycle is interesting because it basically exists as two interconnected subcycles. You have a biological carbon cycle, which is dependent solely on biological processes. And then you have a biogeochemical carbon cycle, which is dependent on geological and chemical processes as well. So if we look at this, the biological carbon cycle is relatively easy to conceptualize. What that basically is photosynthesizers taking CO2 out of the air, consumers eating those photosynthesizers and breathing that CO2 back into the air, which gets taken out by more photosynthesizers. So the biological carbon cycle is basically just the balance between photosynthesis and respiration. The biogeochemical carbon cycle includes a lot more interactions, things like carbon sequestered in the soil in the form of rocks or in the oceans, things like that. So the biogeochemical carbon cycle also moves much more slowly. Biological carbon cycle, you can have atoms of carbon passing through that cycle several times in a day. In the biogeochemical carbon cycle, where it depends on fossilized carbon and uplifting of rock and things like that, that may take centuries or millennia or even longer. So one is much faster than the other. Does anyone have any questions on that?
So the biogeochemical cycle for carbon, that was first before life, right?
Yeah, that existed before life. Now, we've also really upset the balance of both the biological and biogeochemical carbon cycles with our own actions by digging up all this carbon that's sequestered beneath the surface of the earth in fossils and burning it, or releasing that into the atmosphere. By cutting down massive amounts of trees and usually burning them, we're not only releasing more carbon in, but we're also reducing the ability of the earth to remove carbon from the atmosphere. So we've been able to really heavily modify the balance of both the biological and biogeochemical carbon cycles. Any questions on this one? The nitrogen cycle. This one's also important because nitrogen is necessary for proteins. It's one of the main chemical ingredients in an amino acid molecule. Now, nitrogen is very abundant on Earth in the form of pure N2 or nitrogen gas. It makes up over 70% of Earth's atmosphere. This cycle is really interesting though, because N2 gas is not usable by most organisms. Those two nitrogen atoms in that molecule are held together by 3 covalent bonds. They're relatively difficult to split apart. So plants can't just absorb nitrogen out of the atmosphere like they can carbon. They don't have any mechanism for breaking it down into a useful form. So in this case, it depends on something that we call nitrogen-fixing bacteria. So there are bacteria that are capable of using atmospheric nitrogen and converting it into the macromolecules within their own tissues. Eventually, that nitrogen that gets fixed by the nitrogen-fixing bacteria can be taken up by plants, can be consumed by other animals, and eventually it will be returned to nitrogen gas by a series of more reactions carried out by bacteria. I'm not going to make you guys memorize this stuff, but organic nitrogen gets converted into ammonium, which then gets converted into nitrites, which then gets converted into nitrates, which then gets converted back into N2 or nitrogen gas. You don't have to remember all those steps, I just wanted you to have some appreciation for how complex this whole thing is.
With organic nitrogen, is that the nitrogen that we find inside the soil?
So, sometimes, but not always, generally organic nitrogen is going to be sequestered in the tissues of some living organism, or some recently killed organism. So, nitrogen is usually found in organisms in the form of the NH2 or amine groups in amino acid molecules. By the time it's in the soil, usually it's already going through the denitrification process, being converted into nitrates, nitrites, etc. Eventually, yes. Eventually, those nitrates will be converted into pure N2. Well, all nitrogen is natural nitrogen, but the most abundant stores of nitrogen is in the atmosphere as N2 gas. So when it's ammonium or when it's nitrites or nitrates, it's bound to other elements. So ammonium is NH3, nitrites, I think, are NO3, and nitrates are NO4. Anyway, you don't need to know this stuff. I'm just trying to make the concept a little bit more understandable. Now the cycle itself has this big atmospheric reservoir of nitrogen gas, and there's all these interactions. The nitrogen cycle is very complex. I'm not going to make you guys memorize all these interactions. I just want you to understand that it's very complicated and it's highly reliant on bacteria. The phosphorus cycle is another important nutrient. We need phosphorus to make nucleic acids. We need phosphorus to make cell membranes. We need phosphorus to make our bones, form calcium phosphate. This one is often the limiting factor in ecosystems, limiting factor for growth of organisms, because even though we only need very small amounts of it, it's usually only available in extremely small amounts as well. One of the reasons for this is that the phosphorus cycle is extremely slow, and there's no substantial atmospheric component to the phosphorus cycle. It's somewhat unique among these biogeochemical cycles in that phosphorus naturally really never exists as a gas. There are small atmospheric components in the form of like volcanic ash and things like that, but for the most part, the phosphorus cycle depends on the very slow erosion of rock to release phosphates into the ground, which can then be taken up by organisms. So if we're looking at the phosphorus cycle here, you see there's really not much of an atmospheric component. It can be briefly aerosolized in volcanoes, but it's not really a true gas. Mainly, it ends up coming from erosion of rock. It will eventually run off into the marine ecosystem, where it will sink to the bottom of the ocean and be very gradually made back into new rock, which will very gradually be uplifted to the surface, where it can be very gradually eroded again by weathering processes. So you can see how this one takes a really long time, and how it can easily become a limiting factor in any given ecosystem. Sort of an interesting side effect of that is whenever there's an increased release of phosphorus into the marine ecosystem, suddenly it's not the limiting factor anymore, and growth of algae explodes. This tends to happen when we overuse fertilizers on our agricultural lands. So if you look around the mouth of the Mississippi River in the Gulf of Mexico, you find an enormous dead zone, because you have all of this phosphorus from fertilizers running down the river and out into the ocean, allowing explosive growth of algae. Then once those algae use up all the extra phosphorus, they all die. And then they have to be decomposed by bacteria, which use up all the oxygen. So now there's no oxygen in the water and everything dies. That's something called eutrophication. It's an interesting phenomenon that we see because we're able to manipulate the amounts of some of these important nutrients in various ecosystems. Now the last one we're going into is the sulfur cycle. Sulfur is important in the formation of proteins. It's necessary for the formation of an amino acid called cysteine. And it enters the atmosphere in 3 different ways. Naturally by decomposition of organic molecules, or by volcanic activity, and unnaturally by the burning of fossil fuels. So burning coal, for instance, releases a lot of sulfur into the atmosphere. That sulfur then gets deposited through either direct fallout onto the land, precipitation in the form of rain or snow, weathering of rocks, and also released from geothermal vents. Now when I say deposited through precipitation, in natural ecosystems, that's generally in very small amounts. But when we're burning huge amounts of coal somewhere, then we release so much sulfur into the atmosphere that it highly acidifies the water condensing clouds and comes down as acid rain or acid snow. In some extreme cases, the pH of that precipitation gets low enough that it causes extensive tissue damage to plants in the area that can't get out of the rain. Come on. So once again, we have this cycle here. We see in atmospheric components, sulfur can exist as sulfur dioxide, that is a gas. Precipitates through rain or snow, or from volcanic eruptions, then it can just kind of settle onto the land. You see a lot of the same things with this cycle that you see with everything else, where it sort of starts in the atmosphere, ends up in the ocean, gets recycled back up through various processes. So you don't have to know the specifics of each cycle, but you should know the general things they have in common. All right, does anyone have any questions on these biogeochemical cycles? Got just a few more things to get through, and I may have just barely enough time to do it. So terrestrial biomes. If you're really curious about these, the book goes into a lot of detail about it, but I don't think it's really important for you guys to memorize all the different types of biomes and all the different defining characteristics of each one. But we divide up our terrestrial ecosystem into 8 different biome types, just for the ease of classification. Most important among the characteristics that we use to classify them are things like temperature and precipitation. Obviously, the temperature of an ecosystem or the amount of precipitation in the ecosystem plays greatly into determining how much life or what kind of life that ecosystem can support. So this is just a map of the world divided up by biome. And there it is again. very large. So terrestrial biomes, one of the more iconic types is tropical rainforests. Anybody here ever been to a tropical rainforest? If you haven't, you should. They're really cool. They look awesome like that with these, huge dense green forests and picturesque tropical waterfalls and warm ponds for swimming in. They're generally characterized by warmer temperatures and quite a bit of rain. We also have temperate rainforests. This is something you'd be familiar with if you've been anywhere around Portland. These are generally cool with lots of rain. A different type of biome would be deserts. What usually characterizes deserts? They're very dry. They're also often quite warm, but not always. The main defining characteristic of deserts is just lack of precipitation. You can also have very cold deserts. Most of Antarctica is considered a desert because there's almost no precipitation there. So this is just some broad types of biomes and some of the characteristics that define them. Anybody know what type of biome we live in here?
Coastal.
It's not a biome.
It is.
Not a desert, but it's close. So we live in something called chaparral. This is actually one of the rarest biomes on Earth. And it exists only in, I think, 3 areas that I'm aware of. It's the southwestern coastal area of the United States, around the Mediterranean Sea in Europe, and then there's a small area of chaparral in Australia. So this only exists in coastal regions. And one of the main characteristics of chaparral is they have moderate amounts of rainfall, but it occurs almost exclusively in the winter. The summers tend to be extremely dry and usually quite hot. So this shapes the ecosystem because you have to have plants that can tolerate long periods of dryness. Turns out chaparral is primarily dominated by shrubs, although there are also some small scrubby trees. Another characteristic is chaparral biomes are well adapted to periodic fires. We've seen more severe ones lately around here than we normally have, but it's quite normal for there to be fires every once in a while around here. In fact, some of the plant species that live in chaparral are so well adapted to fires that their seeds won't germinate until they've been exposed to fire. So fire is a necessary part of some ecosystems. It's supposed to happen periodically, just not quite as severely as it has been happening around here lately. Ironically, the harder you work to prevent periodic fires, the more severe the fires are when they happen. Because when a small fire comes through, it's going to clear out a little bit of brush, and it's going to burn itself out fairly soon. When you prevent those small fires, that dry brush just builds up and builds up, creating more fuel for the fire that's eventually going to happen, and then they start to get much more out of control. Any questions on chaparral before we move on? Southern California is not supposed to be as green as it is. We're piping in a lot of water from surrounding areas and depleting water sources from all over the southwestern U.S. And eventually the chickens are going to come home to roost. It'll be interesting to see what happens then. If you want to see what Southern California is supposed to look like on the coastal areas, go down in between like San Clemente and Oceanside. That's what chaparral is supposed to look like. All right, marine biomes. I'll just touch on these real quick. So marine biomes are also affected by abiotic factors, just like terrestrial biomes are. What do you suppose is not a big factor in marine biomes?
Air.
I'm more looking at water. So water is never going to be a limiting factor in the ocean. There's always going to be plenty of water. That's one of the biggest things that separates the terrestrial biomes is how much water they get. With marine biomes, obviously that's not an issue.
Light.
Yeah, that's a big one. Light is actually one of the determining factors between the boundaries in different zones of the ocean. Also things like temperature, things like dissolved oxygen content in the water, various dissolved nutrients. So these are all abiotic factors that affect marine biomes. And you can divide up the ocean into several different ways depending on what you're looking at. So the 3 main biomes in the marine area or the sea would include the intertidal zone, the pelagic realm, and the benthic realm. Benthic realm being at the bottom, pelagic being open ocean, intertidal being intertidal. Come on. You can also divide it up into the intertidal, neritic, and oceanic. So the intertidal is just where the tides affect it. The neritic zone extends roughly out to the end of the continental shelf where it's still fairly shallow, and if water is clear, light can penetrate all the way to the bottom. The oceanic zone is beyond the edge of the continental shelf where it gets very, very deep, and light does not penetrate all the way down. Speaking of light, that's what we use to classify the photic and aphotic zones. Photic zone being as deep as light can penetrate in the ocean. Now obviously that's not going to be a uniform depth everywhere in the world, because based on how murky the water is, the photic zone may be shallower or deeper. Below the photic zone, we have the aphotic zone where light does not extend. And then the extremely deep ocean we call the abyssal zone. That can be incredibly deep. Oh, that's all I got today. All right, great. Anyone have any questions on this stuff? Ended just about the perfect time. Office hours will be starting right now. Be prepared on Thursday for a very brief lecture and then a lot of review. The review is going to be primarily student-driven, so come prepared with questions to ask. You will be much more productive if you've done a little bit of studying by then, yes. I hope so. Some of them already are, I think, but I'll try to get most of them up by tomorrow. Failing that, they will absolutely be up by the weekend.